Hi, today I'd like to walk you through a few small steps we can take and that I am currently taking in my program to improve asteroid photometry and light curve generation from that photometry. Let's first talk about what problem we're trying to solve. We have a number of image files taken from one session. Now, a session is typically defined as one observer taking one night of images on one asteroid. So these image files are going to be very similar to each other, but you will see the asteroid move slightly from image to image as they're taken during one night. Now, what we want to accomplish is first aperture photometry to find out what the magnitude on a catalog basis we are observing for that asteroid image to image over time during the night. And then we want to merge light curves from several sessions by rotational phase to determine what the rotation rate is, the shape of the light curve, and a number of other factors, including the phase angle dependence G value. The light curve on the right is pieced together from several nights, and it arises in the increasing and decreasing brightness of the asteroid as viewed from Earth, because the asteroid is rotating and producing a changing cross section of reflection of sunlight to Earth to your telescope. So again, we're looking at multiple sessions to make an asteroid light curve over one apparition, and I call a series of sessions during one apparition on one asteroid a campaign. And the difference between an apparition and a campaign is that an apparition is the close approach of Earth to an asteroid and vice versa. Uh, so it's a function of the asteroid. A campaign is what you do about it, is you're taking action. When everything works, the light curve can look like this. This is a recently taken light curve for my program. And you can see that it has a complex shape and it has a very accurately, very precisely determined period. And the reason you can get such a precisely determined period is that you're taking data over several weeks. And if you don't lose count of the cycles, you get to divide the time uncertainty by the number of cycles to give a very precisely determined period. One of the things we want to know about all these asteroids is whether their periods are changing. And another light curve. This one's more difficult because its period is close to 1/3 of one sidereal day, meaning that it's very hard to get complete coverage. In this case, it was accomplished by taking data over 4 weeks. So that's basically what we're trying to accomplish, is to get from a series of images to a light curve, and I'll show you beyond. So let's talk about small improvements. They are categorized, I categorize them for the purposes of this talk in 4 directions. Session planning, which happens the day before you ever take your images. Which asteroids do you want to image, and how do you want to image them? Then when you have the data, how do you choose the catalog comp stars, comparison stars? I've made some changes in how I do that. I want to tell you about those. The aperture photometry per se, and light curve construction, which is not part of the aperture photometry of my title, but we should cover it anyway. A number of improvements in each of these categories. I won't go through this now because we'll go through each one rapidly. So fasten your seatbelts. We have a lot to cover. Let's go. First, session planning. I have started using the digitized sky survey to avoid background stars behind my asteroids. I don't have any control over the stars of the asteroids, but I do have control over when I take photographs of this moving asteroid. Now, this is the Palomar-based digitized sky survey, not the Sloan digital sky survey, just to be clear. Now, if you work in the SkyX software, one of their advanced editions, uh, you put in the date and time, UTC, that you want to cover, the asteroid identifier, and you will get this in the vicinity of the asteroid, you will get the stars that may well conflict with your aperture photometry, but you only get the bright ones. If you want more, you can use the digitized sky survey plugin in the SkyX, and you do it in this order. You clear all the stars, you get the field of view from the sky chart that you're currently viewing, and number three, you fill the sky chart with the digitized photograph from the DSS, and you get a much more detailed view of the background stars that your asteroid is likely to cross as a function of time. And then you can simply scroll the time back and forth and see during what time periods you are likeliest to be clear of background stars when you take your asteroid photographs. So that's the DSS and how I've started using it. It gives much greater efficiency by releasing the time where I would have star conflicts to other asteroids that don't. Session planning. Oh, this one is easy. If you have a period of 8 hours that you're expecting, take a photograph every 8 minutes. Now, eventually, you may change that, but that's how you would start off your first few nights in a given campaign of sessions. This results in very nice phase coverage, especially when you're just trying to get the shape and period. In the best case is when you have a bright asteroid or a long period leaving observation gaps, time gaps between your images, during which time you can slew to some other asteroid and image that. I have recently been interleaving up to 5 asteroids, moving among them in a cycle to great efficiency effect. And it's easy to use this rule of thumb, except when it's not. When you have a faint asteroid with a short period, you're going to have a problem applying this because your cadence needs to be faster than you can possibly take images at long exposure times for this faint asteroid. In this example, I have a period of about 4 hours, but I needed 15 minutes exposure time to get these images with decent signal to noise for this magnitude 17 or 18 asteroid, but I managed to get it anyway. Now, when you're session planning, you often have a choice between time periods which will fill gaps in your building phase diagram versus getting overlaps where you have multiple nights filling the same phase region in your light curve. To fill gaps is important, especially early in the campaign. You need to prevent bad Fourier fits to data points. Where you have gaps, you can get fits by exclusion, which are pretty deadly because they are guaranteed to give you a bad light curve and aliasing to boot. You want to prevent aliasing, which are multiple Fourier solutions almost equally good, which means you have a beautiful light curve and fit, but really an indeterminate period. It improves the shape determinations and aesthetics as well. But you do need some overlaps as you build your light curve for confidence in your Fourier solution, especially for long periods where you probably are not going to get overlaps unless you intend to get them. You can also more easily distinguish any noise from tumbling, real light curve changes, and so on. Also, you need overlaps to determine G, the phase angle dependence of magnitude, so that your sessions match in magnitude. And this requires that you get multiple sessions with overlaps at various phase angles. But it is typically done. So in practice, I start by filling gaps in a building light curve. Then in later sessions, also try to get at least 2 overlaps at differing phase angle. That's my practice. In the next category, how we handle the catalog and comparison stars. I have gone to much stricter screening of my comp stars. Last year at SAS, I told you that I was using up to 200 comp stars per image. I don't do that anymore. I find it's better to more strictly screen them and then use a much stricter set of quality screened comp stars and comp stars that much more closely match the magnitude and color of the asteroid target. So I'm down to typically 20, 30, 40 comp stars, sometimes as few as a dozen, where I was using up to 200 last year. I use fewer comp stars, but much more closely matching the asteroid. That's a simple case. The next improvement in catalog and comp star handling was prompted by this effect from last September 2020. We all remember how bad the skies got in the western United States. Now, this is not an observable sky, but even 800 miles downwind in northern New Mexico, where I observe, we had our share of pretty terrible skies. But I was determined to keep observing. And I was able to find a source of error that could be eradicated. And I want to tell you about that because it's pretty unorthodox. Per observation, not per image, air mass calculations. Yes, really. So if you're looking west in the northern hemisphere, your field of view is probably going to look like this. North is, of course, pointing toward the north celestial pole. So you have a top corner, highest above the horizon, and a bottom corner, lowest with respect to the horizon. And if the span of your field of view from corner to corner is your typical amateur 40 arc minutes, then the difference in air mass top to bottom is about 0.04. Now that doesn't sound like much, and under our good high altitude clear skies, it amounts to about 6 millimagnitudes difference in extinction from top to bottom. Pretty manageable. However, if you have a lot of smoke with extinction coefficients up to 0.5 or 0.7, this is a top to bottom difference in light extinction of 20 to 28 millimagnitudes. And this is pretty terrible against a catalog with a stated and experimentally confirmed error of about 8 to 10 millimagnitudes. So what I did was, instead of using the typical per image air mass of the center of the image, I had started computing air masses separately for each comp star and each asteroid's sky position in each image. Takes a fair amount of computer time to do it. It's not that hard, and it really completely suppressed the edge-to-edge extinction errors that I was seeing that were dominating. And I continued to take images and get good, usable, light curve ready photometry results up to about 0.7 extinction, which at 30 degrees elevation above the horizon, only 1/4 of the light hitting the top of the atmosphere is getting through the atmosphere. Still, it worked very well. So I continue to use this fairly important improvement in photometry on all my images now, good sky or bad sky. Now, for aperture photometry proper, let's talk about a strangely shaped aperture for asteroids. And it arises because of this. This is a very, very small expanded section of one image. The comp star on the left has a very nice, round, tightly focused flux profile, and you can put a nice round aperture around it to integrate all of the light from that comp star. But you can't do that necessarily in the same way for the asteroid because it's moving and its photons are being strewn along the path that that asteroid is taking, even inside one image. And the result of using this small round aperture for asteroids in the same image is catastrophic, because you will lose the front and back photons, and you will lose it to an extent that varies from image to image. So what you set up is a pill-shaped aperture. If somebody has a better name for this, please let me know, but that's what I'm calling it for now. And it's constructed by strict analogy with the manner of making apertures for comp stars. For comp stars, you simply take all the pixels within some radius r of this central point, perhaps the centroid of the light flux. For asteroids, you take all the pixels within that same radius of the motion line segment, from the center of the asteroid light flux when the image starts to the centroid when the image ends. That's a short line segment, and you simply take all the pixels within the same radius that you used to construct the round apertures for comp stars. And it can be pretty readily constructed as two end circles congruent with the comp star aperture and all the pixels in between. In other words, the union of two end circles and one mid-rectangle. Surprisingly, all of these items can be formed using dot products and multiplication, no sines or cosines, no transcendental functions at all. So its computation is pretty rapid. The statistics, the signal to noise does suffer a little bit, but that's unavoidable. It's not a fault of the aperture shape that gets larger for asteroids. It's the fault of the physical fact that the asteroid is actually stringing the photons over more pixels. But you do gain much more than you lose in statistics by eliminating the asteroid flux clipping. This is working extraordinarily well, even for fairly fast asteroids. Now, that's how you get the central aperture accurately. How do you handle the sky background? Second aperture photometry improvement. The shaded areas around the central apertures are the pixels used to estimate the local sky background. And it's not that hard to collect all the different pixel values, the ADUs or intensities of each pixel, but then how do you get one best estimate to subtract from the aperture pixels? How do you combine all those pixel values into one best estimate? Well, there are some historical ways to do this. The mean is universally recognized as the worst possible way to do it, because every hot pixel, every neighboring star, every gradient, every cosmic ray is going to catastrophically change the mean in ways that you really can't compensate for. Median of all the ADUs in the annulus around the aperture is better. It rejects, to some extent, outlying pixels. Sigma reject first and then take the median is better still by a long shot. And that's what a lot of commercial software does. What I found are facilities in Python packages to do an iterative sigma reject and median. This is iterative. You do a sigma rejection, take the median, do another sigma rejection, take the median. I cycle it between 3 and 5 times, and you get an extraordinary rejection of cosmic rays, nearby stars, and all that nonsense. In simulations where I start by actually making pixels with a lot of different kinds of statistical and systematic noise, I keep getting accuracies of 1 ADU or better. So I have adopted this for all my aperture photometry for both comp stars and asteroids, and I'm very happy I did. This is working very well. Very quickly, I use diagnostic plots that I used last year as my next improvement in a much stricter way than I was able to do before. What's happening is that the automated screening of comp stars that I mentioned earlier brings the errors down so far that remaining outliers, typically from catalog errors, jump out much more dramatically. Here are a series of very good diagnostic plots. You have time across the bottom and difference from its peer comp stars in the vertical direction. And you can see these are all very well behaved. Those are all good comp stars that will get used, but there are occasional outliers. That's a magnitude error in the catalog. It's systematically different by a large extent. So you get rid of that comp star before you do your regressions. This is a variable comp star that was not marked as such in the catalog. Now, we do call out in the initial automated screening all the stars marked as variable. Those are removed, but occasionally you get a truly variable star that was not caught during the construction of the Atlas catalog. We get it here. And then occasionally, of course, you have an image artifact where you have something that happened to a given observation, whether the aperture or the annulus, and you simply have to get rid of those data points. But the noise is so suppressed by the early stricter screening that these jump out much more readily, and you can at your discretion remove these. So those are the aperture photometry improvements I want to talk about. Lastly, light curve construction is not strictly speaking part of aperture photometry, but it needs to be covered here because I have a couple of improvements. The prior improvements have led to a condition where I need not make any nightly 0-point adjustments. My last 30 or so light curves that have been completed have needed none of these whatsoever. And the benefits are that you get objective matching rather than manual subjective matching of the magnitudes between sessions. And it's particularly useful when the asteroid in question has a long period where the session data do simply not overlap in phase, and you're at the mercy of the absolute magnitudes, not just relative magnitudes matching. When you have low amplitudes where bad matching between sessions can completely overwhelm the signals that you're looking for, and we're down to, I'm looking now at light curves of 30 to 50 millimagnitudes, so we're beginning to encroach upon exoplanet style territory. And another benefit is in better detection of systematic non-endial behavior, where you have real changes possibly in the light curve during a given apparition, or you have precession called tumbling, which gives you a non-single Fourier solution, or binary asteroids. Lack of need to make subjective 0-point adjustments makes these things much easier to handle. There are some exceptions. I have to still make 0-point adjustments whenever I have sessions at very low phase angle because of anomalous reflection. Anomalous reflection you already know about when you shine a flashlight at night against a car tag or a road sign, or your headlights intercept one of them, you get more reflection than you expect to get. That's because of the shape of the particles in the car tags and the reflecting road signs. Now, those are intentional, but the same kinds of things can happen at the physical surface of the asteroid. So you can get more light than you expect at these very low phase angles. It does require a manual 0-point adjustment, but highly constrained, only to those sessions, only to lower magnitudes, brighter observed magnitude, and it must be monotonic with the absolute value of alpha, and again, only at small phase angles. So it's not a terrible exception, but it needs to be kept in mind for some asteroids. One other almost trivial exception is in G adjustments, which are strictly speaking 0-point adjustments, but are so constrained, only one value across an entire campaign, across an entire light curve, and it has a physical basis. So that's not really anything but a trivial exception, but I'll note it here. And by the way, how do you get these phase angle dependence G values from the HG model? Well, you get them from a series of trial Fourier fits, each of which you manually adjust in, for example, Canopa's software, the G value, and you look at the best Fourier error or root mean square error given that G. And you almost always get a curve very much of this shape. Given these conditions, the sessions, of course, must vary in phase angle or there's no G dependence to talk about. Each fit, you really should use the same sessions, the same period range, the same Fourier order, and all the period estimates have to match. No fits by exclusion. And another requirement is observer patience. But you just make a pot of coffee and get it done. With the result that when I determine G values, most of them differ from the minor planet center's stated default of 0.15. Most of them differ. So 0.15 is a fine default to use when you're just getting started with a new light curve and you have no other G value to work with, but you'll find that after your light curve is perhaps half completed, you need to start looking for that G value as you build your light curve. One last thing, a bonus. How do I close this campaign? When should I close it? Now, here are some unhappy endings to light curve campaigns. You get to the end of the apparition and you simply can't take any more data, or you just can't get a reasonable Fourier fit. Now, for the first two of these unreasonable Fourier fit conditions, where you have tumbling or a binary asteroid and you're not prepared to handle these, my recommendation is to get some help from somebody who's published these kinds of asteroid light curves in the Minor Planet Bulletin. Get their help. They might even help you observe this thing before the apparition's over. Sometimes the real light curve is changing faster than you can take data, maybe because of weather. And sometimes, as my high school basketball coach would say, sometimes you just may not can. So those are unhappy ends to a light curve campaign. But look, if you have good sessions that you've taken, upload your good magnitude data to the asteroid light curve database anyway. Maybe somebody in future apparitions will find out what your data meant. Maybe you will. But happier is when you can get a complete light curve and publish it. This one's not ready. It has phase gaps. It has a credible shape, but it's still got aliases here in the period spectrum. That's not going to do. So you need to get more data and wait for it. Here's a worst case where you have not only phase gaps and aliases, but your shape is not credible. This maximum is probably not real. This one is probably not real. Beware the fit by exclusion. When you get a fit by exclusion like this, where you get a nice looking Fourier fit only because you have huge phase gaps, don't believe it. Get more data or get help. Do something different. But this is what you're looking for. A nice, complete light curve, no phase gaps, a credible shape, no aliases, no credible aliases differing in period from this best solution. And you are ready. This one's ready to publish. Congratulations. Do publish it, please, in the Minor Planet Bulletin. So this is the happy ending we all want. Thank you very much for listening to my extremely rapid romp through all these impressions, all these improvements. Best of luck to you all. Clear skies. Thank you.